Okay, here we have a binomial distribution where x belongs from a binomial distribution with n being 10 and the probability of success being 0.25. If I just click here, you can see a histogram here of the probability distribution which follows that. But what we're going to do, we're going to sample from it and do the sample mean. And I can take different size samples. I'm going to take a sample size of 4, 8, 10, 20 and 100 in this case. Now, in order to, what is surprising that any distribution, if you have more than a certain number, we'll talk about that certain number later, then it will conform to a normal distribution. So what you do is you take your sample 4, you calculate the mean, and then the means are then distributed in a certain way. They are always going to be distributed with a mean of mu and a variance of sigma squared over n. So the mean of a binomial distribution is np, which n in this case is not the same as the sample size, it's the number of trials. So it's 10 times 0.25, okay, which gives me 2.5, and the variance is going to be 10 times 0.25 times 0.75, but I need to divide that by the number of in the sample that I'm going to take. So the sample sizes are going to change for 4, 8, 10, 20 and 100. So I'm just going to get rid of this probability distribution function. If I click when n is equal to 4, and this is from some data that I've already collected, and I've made a sort of a histogram of the different means that I've got, okay, and if I move the slider so that n is equal to 4, okay, this is a normal distribution which has a mean of 2.5 and a variance of 1.875 divided by 4. This is what the effect of n doing. Okay, it's looking fairly normal, but not quite there. If I now click n is 8, it's looking a bit more normal, and then move this so that I got n is 8. Okay, I can repeat the process, and then when n is 10, okay, it's looking more normal. When n is 20, so move this up to 20, looking normal, and then when n is 100, okay, and move that right to the end, you can see that it will fit fairly well. Okay, so what we had to do is arrange so that the sum of these bars, the area underneath the bars, was equal to 1, hence it's a relative frequency density taken from the sample means. Okay, and the same is also true. Let's do look at a Poisson distribution as well. Okay, so this is a binomial distribution. We're now going to look at a Poisson distribution. We have the same thing here. Now we have a Poisson distribution. Lambda or m is the parameter. We're going to have a Poisson distribution 4. Okay, and if you want to see that Poisson distribution before we actually sample for it, it would look like that, the histogram. It probably wouldn't be joined up because it's a discrete random variable. Okay, if the variance and the mean from a Poisson distribution are 4 and 4, and therefore if you're going to take, like again, we're going to take different sample sizes, calculate the sample mean, okay, and then check what happens when we keep that sample size to 4, 8, 10, 20 and 30 this time. So these will be normally distributed with a mean of mu, so the mean will also be 4, and the variance will be 4, which I'm going to write as 2 squared, and I have to divide it by the sample size. Okay, so it's going to get rid of the original distribution. If I now click, this is what happens when the sample size was 4. So I'm taking 4 things out, and I'm finding the mean, and I did that. I did that 100 times with this sort of data. So if I move this so we get 4, so this is the normal distribution goes with that. It's looking okay, but not really like a normal distribution. So change it to 8. Okay, it's getting more like it. And change it to 10, a bit more like it, and then change it to 20. Okay, a bit like it, and then change it to 30. Okay, looking a bit more like it. Okay, and basically there's this theorem that says if the sample size is 30 or more and it's from a non-normal population, then the distribution of the sample mean will be normally distributed with a mean mu, which can be calculated from the original distribution, and a variance of sigma squared. Sigma squared can be calculated from the distribution, which is 4 in this case, divided by the sample size. And normally the rule of thumb, if it's more than 30, you can use the you can say that it will be distributed this way. Right, let's just have a look at that theorem in a bit more detail. Okay, it's called the central limit theorem. It's quite important in statistics. From the diagrams that we just looked at, you can see that samples were taken from populations which were not normally, i.e. one was binomial and one was Poisson. The sampling distribution takes on a characteristic normal shape as the sample size increases. Now, for large n, the distribution of the sample mean is approximately normal, and the word large means more than 30 in the sample size. That means you're taking 30 things out, sampling 30 things out, and then calculating the mean of that. This result is known as the central limit theorem. It's somewhat surprising since it holds when a population is discrete, binomial or Poisson that we did, and also hold if the original population is continuous, like a uniform distribution, although I didn't do a GeoGebra applet for that because it's not in our course. So the theorem says this: for samples taken from a non-normal population with mean mu and variance sigma squared, by the central limit theorem, the sample mean will be distributed as normal with a mean mu and a variance as the variance calculated from the non-normal population divided by the sample size, provided that the sample size is large and the rule of thumb is that n is normally more than 30. Okay, and this is known as the central limit theorem.